So we're still dealing with binomial distribution, binomial probability. And remember, n, we have a thing, n is how many numbers are there in our data. Remember, what's our n? We're going to be using that a lot. Our p, the probability of success. All right, we know that LeBron James is 74% accurate at shooting free throws, so the probability of success is 0.74. However, we've been also dealing with Q, so let me remind you, Q is a probability of failure. If LeBron James shoots 74% of his free throws, he misses 26% or 0.26. Okay, so now with this binomial, we're going to be able to figure out what's the mean, what's the expected value. And it's going to be pretty simple. The formula for the mean is going to be n times the probability of success. So n times p. So an example, let's take a look. LeBron James is 74% accurate at shooting free throws. Out of 20 attempts, how many shots is he expected to make? So n, he's going to be shooting 20 times. Probability of success is 0.74. Probability of failure is 0.26. One thing I want to emphasize still, P plus Q, success plus failure should equal to 1. Okay. Now, how many shots is he expected to make? I'm just going to go 20 times 0.74. And I'm going to go how many times the probability of success. Now, use a calculator necessary. This thing is going to tell me 14.8. He is expected to make 14.8 shots. Now, mathematically speaking, I will call it 14.8. And as a matter of fact, on the homework, I will even tell you round it to 1 decimal place or round it to the nearest 10th, right? So that means 1 decimal place. Mathematically speaking, we said he's going to make 14.8 shots. Now, not mathematically, but just normal speaking, we're going to say, well, he cannot make 0.8 shots, right? He either makes 14 or he makes 15. So if we're speaking with people, we're like, he's expected to make 15 shots or 14 shots. 14 or 15, you should be okay. Mathematically, we say 14.8. Now, there's also the variance. We can also find the variance. Just a reminder on our mean. Remember, I introduced you guys a few weeks before. A few weeks ago, I introduced you guys to the Greek alphabet, or at least a few letters from the Greek alphabet. And then for mean, I use the letter mu. Do you remember how the letter mu looks like? Okay, mean, it's mu, which it looks like a U, but one side is longer than the other. So it's not that I got crazy and my left side was too big. That is how mu looks like, okay? So I didn't go crazy. I also introduced you guys to what we call variance. Let me just go here, variance. Let me add a variance to our notes. And standard deviation. Do you remember the Greek letters for that? Okay, variance looks like this to the second power, sigma squared. Standard deviation is just sigma. So when we get the variance, right, notice how variance is sigma squared, but standard deviation is just sigma. When we get the variance, just get the square root of that. So let me give you a couple formulas. What's the formula for variance, Mr. Leonzo? All right, good thing you asked. Formula for variance. Again, we know our n, we know our p, we know our q. Is going to be the product of all three. So variance is going to be N times P times Q. And for standard deviation, I might ask you for that, is basically the variance, N times P times Q, and then get the square root of that. Okay, so here, let me figure out our variance in my example. What is my variance? I'm just going to go 20 times 0.74 times 0.26. 20 times 0.74 times 0.26. I get 3.848. I might even ask you, round this to to 2 decimal numbers, or round it to 3 decimal numbers. You will be given instructions on your homework. But right now, let me just call it 3.848. I might need to round it to whatever's necessary. Now, what's the standard deviation? Well, I'm just going to say it's the square root of 3.848. In this case, let me use my calculator, and it goes to about 1.9616 and somewhere. Again, I will ask you to round it to 2 decimal places, 3 decimal places, 4 decimal places. So make sure you guys read the instructions, how many decimal places I ask. So LeBron James is 74% accurate at shooting free throws out of 20 attempts. What is the standard deviation? We just answered 1.9616. Okay, you might be like, what is this even fun? How? This is pretty boring, Mr. Leonzo. How is this even interesting? Oh, good thing you ask. Now, remember how back in the days I introduced you to what we call the normal distribution that looked like almost like a bell shape. Remember that figured? And then I said in the center we have our mu. We have our expected value. Now, if I go from my expected value, so I go 1 mu minus 1 standard deviation, and then 1 mu plus 1 standard deviation. Remember that I said that distance, my numbers in between my space there will be covering 68% of my data. Remember when we call this the empirical method, remember? Does that ring a bell? And then I said, well, what if I increase my bracket here? What if I go 1 mu minus 2 standard deviation, and on the right I go 1 mu plus 2 standard deviation? Oh, well, remember I mentioned that is 95% of our population, 95% of our data. And then I even increased it more. I'm like, all right, let me increase my my space here. What if I go 1 mu minus 3 standard deviation, and now here I go 1 mu plus 3 standard deviation? Then I will tell you, oh, that's 99.7% of our data. All right, so now for accuracy, we know LeBron James is 74% accurate. I just found out that he's expected, he's expected to make 14.8 shots. So I'm going to say, ooh, my mu here is going to be 14.8, my expected value. But I just also learned that my standard deviation is 1.9616. Now, if I asked you, let's say 95% of his shots. I'm gonna say 95% sure that he's gonna make how many shots? So 95%. Okay, so I have to go this bracket. U minus 2 sigma notations to U plus 2 sigma notations. So I'm gonna say, let me have my bracket. For my first number, I'm gonna start with 14.8 and I'm gonna subtract 1.9616 twice. Because it's mu minus 2 standard deviations. Okay, so, and let me round my answers. I have a long decimal in my calculator, but let me round my answer to 2 decimal places, all right? So the expected value minus the standard deviation twice, I happen to have 10.88. So you should do it on your calculator. So you should do it so to see what number I got. Now let me start again for my mu, which is 14.8. But in this case, I'm gonna add standard deviation twice. Yeah, again, let me round this to 2 decimal places. I'm gonna get 18.72. So I just added this part. That's why I did the work from our notes on the space above. I left this space right here. Okay, so 95%. Remember the percentages of the vertical or the empirical. I call them 68. We did a dash. 95. We did a dash, and then 99.7. So if I ask you 68%, only subtract and add 1 standard deviation. If I ask you 95%, then your bracket goes 2 standard deviations each side. If I ask you for 99.7%, then it's mu minus 3 standard deviations and mu plus 3 standard deviations. Just a review of our empirical method, empirical rule. Okay, cool. That's gonna be fun. Okay, now let's take a look at here. Game fairness. Okay, how things are expected. Now, things are, I'm gonna say, are faired. A game, when we play a game, it is faired if the expected value is 0. Let me do a couple examples here. Okay, and we're not gonna see much on the homework. However, it is for us to understand, for us to know. 2 children are playing with a bag of 4 marbles. One is white, so let me just do something here. Let me write this thing down. We have 1 white, 2 are blue, so let me write 2B, and 1 is red, so 1R. Each child takes a marble from the bag. The child with the red marble receives 3 points. Okay, so the red marble, let's just say he gets +3. Otherwise, the child loses 1 point. Okay, so if he gets a white or a blue, he loses 1 point. Is this game fair? Why or why not? Okay, so let's take a look. What's the probability of getting a white? 1 out of 4, right? So I'm gonna say probability of getting a white is 0.25. However, I'm gonna multiply this by -1. Why by -1? Because the child loses a point if he gets a white. Okay. And then let me add this. Let me add another probability. What's the probability of getting a blue? 0.50, okay. Because there's 2 out of 4. 0.50, and let me multiply this by -1. Why? Because the child loses a point if he gets a blue. Now, what's the probability of getting a red? 0.25, right? Let me multiply this by +3. And the reason why I multiply by +3 is because the child gets 3 points if he gets a red. All right. Now, let me figure out each of these multiplications. 0.25 times a -1. It is negative 0.25. 0.5 times a -1, it's a negative 0.50. Now, positive 0.25 times 3, it's positive 0.75. What does this equal to? If I add them all up, it's equal to 0, right? This case, the game is fair. There's the same amount of chances of winning than losing. At the long run, you should win as many points as you lose. So why is this fair? Because at the long run, you should be expected to be about 0. Like the same amount of points earned are the same amounts of points you lose. Let's take a look at this other one. A game consists of rolling a die with 2 red sides. Okay, so let me write this information down. I'm going to write it here on this other side. 2 red, 1 blue, and 3 green. Okay. A roll of red wins $1. So let me put it +1. You win $1. A roll of blue, you win $6. Oh, nice. You win $6. And a roll of green, you lose. Okay, so you win nothing. You lose. Okay. It costs $2 to play a game. Oh, okay. So let me subtract 2 from each. Technically 1, 0 minus 2. So I'm gonna say if you get a red, you still lose $1 because you paid $2 to play and only made 1 up. So you still lost. If you get a blue, you win $4. And if you get a green, you lose $2. Is this game fair or why or why not? Okay, let's figure out. What's the probability of getting a red? 2 out of 6 or 1 out of 3? So I'm gonna say 0.33. Let me do this as a decimal. 0. Let me do 3 decimals. Why -1? Because you lose. You lose $1 if you get a red. Because you paid $2 to play and you only got 1 back. So you lost $1. Now let's take a look at the blue. What's the probability of winning? You have 1 out of 6. So let me call this 0.167. And let me multiply this by 4. Why? Because if you get a blue, you win $4. Technically, you win 6, but because you paid $2 to play it, you really just won 4. And then let me add it to the probability of green. What's the chance of getting a green? There's 3 greens out of 6 sides, so I'm gonna say 0.5. But I'm gonna multiply this by a -2. Why? Because if you get a green, you lose $2. Right, the $2 that cost you to play. Okay. Multiplied your numbers, add them all up. I'm gonna say that in this case, I end up getting a negative 0.67. Wait a minute, it's not 0. So this game is not fair because the game is not 0. It's a negative 0.67 because the value that gave me is negative. I'm expected to lose. I should be losing about 67 cents each time I play. Like I said, sometimes I might win some money, sometimes I might lose some money, But at the long run, when I see how much each game, how much did if I make it all fair, all even, I'm gonna say the average, I'm expected to lose 67 cents on each game. Yeah, definitely not playing this game. Not good. Okay, so you learn about fairness. We learn about expected value, standard deviations. We remembered about variance. We remember our empirical rule, 68, 95, 99.7. You should be good for your homework now.